Hello, everyone, and thank you for joining us for our presentation on MPC Research Project 637, Optimizing Snow Plowing Operations. The presentation is scheduled to run from 9:30 to 10:30 Central Time or 8:30 to 9:30 Mountain Time. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. And a special thank you to the MPC for providing the resources and the opportunity for this research and presentations like this. Our speaker today is Yen-Hu Wang. He is currently working towards his PhD at the Department of Civil and Environmental Engineering at the University of Utah. He received a master's degree in transportation engineering from Beijing, Zhejiang University, China in 2018. His research interests include traffic modeling, vehicle route optimization, and data-driven facility location optimization. With that, Yen-Hu, I'll go ahead and mute and turn the presentation over to you.
Good morning, everyone. I'm very glad to have this presentation with you. And the topic I'm going to talk about with you is optimizing snow plowing operation in Utah by routing and truck allocation. And this presentation is divided into 4 parts. In the part 1 is introduction, and this part I simply introduce the background and the motivation, the reason why I do this project. And the second one is the snowplow routing optimization. And here we will introduce how we optimize the 12 regions covered in the North Utah. And the second one is that the risk average snowplow allocation. Consider the chance of the truck failure. We need to know the optimal allocation to make sure the service level can be sustained with a certain priority. And the final part is the conclusion. And this part I will conclude what I have done in this presentation. Okay, let's start from the first part, introduction. So do you love snow? Yeah, I like snow because I think the snow makes the world beautiful. Imagine that in the morning you get up and stand by the window, you will see the world outside dressed up with snow. It looks very wonderful. But as a guy majoring transportation engineering, I know this snow is a snowy day. Snow is a bad weather conditions, and it has a negative impact on travel safety. For example, it can cause us longer traveling times. As you can see here, especially on highways, it suggests us to travel lower than annual. So we need to take more times to go to work or go to school. And another reason is that, for example, in this figure, we can see these 2 cars crash. Why? Because I think maybe the first car stopped suddenly, but this car didn't stop completely before hit this one, because this is the reason is that the fraction between the tile and the road surface significantly reduced. So the distance we travel before we stop completely extended significantly. So these 2 reasons caused us that snowy conditions has a bad impact on our traffic conditions. So especially in the city facing a frequent snowstorm, there must be a winter maintenance team which deal with the snow removal operations or road maintenance in the season of winter. So for example, in Utah, the UDOT is responsible for about 658 miles of the state-owned roadways. And especially in Utah, each year may have 25 winter storms. And each storm takes about $1 million for the winter operation. So it's really a big investment. So according to this reason, the bad impact on the travel safety and also the investment in the winter operation, we know that if we can improve the snowplow route and also the snowplow allocation, would improve the efficiency of the snowplow snow remover, and also maintain the safe road conditions, and also maybe reduce the budget in the winter maintenance. So next, so this is the background and the motivation. We wanted to optimize snowplow route and also optimize the snowplow allocation. So next we go to the second part, snowplow route optimization. In this part, we studied the 12 regions within the North Utah. As you can see here in this figure, this includes 12 regions, and the different lines represent the roadways covered by each region. And also, each region has a fleet of snowplowing trucks, which is shown in this figure. As you can see, there are totally 3 plow types used in each region. In the regions in Utah, for a single wing region, each pass this plow can clean 1 lane. And then for the tow plow, it can clean 2 lanes each pass. For the double wings, the capacity is between the single wing and tow plow, maybe 1 lane and half lanes. Is this usually used for clean the highway lanes and the shoulder. And also we can see for some regions it only have 1 type of plow, for example, Oregon. And also for each region, we optimize the roads for each region. And for example, we take the region 8. For instance, we can see here the detailed network is chosen here, and we also marked the lanes for each road segment. For example, for the road lanes, we can see here that for each direction, there are 3 lanes we need to clean. And then for this one, for the blue one, maybe these are local roadways, and they are totally 2 lanes for the 2 directions. And also this figure shows the plow speed, and the different roadways, different road segment has a different plow speed. And the plow speed is assumed to be the 60% or 70% of the speed limit. So this is the network and the plow we used in each region. And then, so in this part, we need to do 2 tasks. The first one, we want to evaluate the efficiency of the UDOT current snowplow while mining the aerial data. This aerial data is a vehicle location data showing how the snowplow trucks, how it moves to clean the lanes. And then we want to design a road that will be more efficient than UDOT current loads. So in order to complete these 2 tasks, we need to implement 3 steps. The first one, aerial data processing, and to evaluate to mining the UDOT current roads. And then we need to do the network editing, giving the roadways, and we want to get to edit the network and to get some information for each road segment and to construct the graph. This is a very key input for the routing algorithm. And then we run our algorithm to optimize the route and also evaluate these 2 steps. The first one is UDOT current routes, and the second one is our proposed route. Okay, so and next I talk about these 3 steps in detail. So this is the roadways provided by the UDOT, and we can see the roadways we need to clean. In this region, Lake Town. This region is Lake Town. And then this figure shows a lot of the green icon. Each point represents the location of the snowplow truck at a certain time. So through visualization of these points from early time to later times, and then we know how these trucks moves around to clean the lanes. So through this step, we know the current routes implemented by UDOT. And then still we use the step is to edit the network to construct a graph. And this is by observing these roadways, we edit the network in ArcGIS Pro. we insert node at interjection at each junction, and then connected user line to connect it to nodes, and then we can get the row segment information. So shown in this table, and this table includes five columns, including the head node index, tail node index, the number of lanes for each of this arc, and the length of this arc, and the traveling times. The second, for example, we look at the first row. It means the row segment from the north to south direction, and then we know this arc has 1 lane in total, and the length of the arc is about 4.12 miles, and the traverse time is about 8 minutes. So and so on and so forth. So after obtaining this row segment information, we can construct a travel cost, which is used in the following step. Okay, and then obtaining this information, and then we want to design a road to clean maybe all the lanes in the network. And in order to simplify this figure, we use a black node to represent the intersection at the upstream, and another black node to represent the intersection at the downstream, and 4 arrows represent the 4 lanes we need to clean. So, and we know that the demand is located at the arc. So this could be formulated as the arc routing problem. But during the past decades, many research work has done focusing on the node routing problems, and also many advanced algorithms can be used directly. So here in this project, we also transform the arc routing problem into node routing problems. How we do it? For example, we just insert a green node between this link to represent the demand node. And then if we can design a route with a minimum cost to visiting all these nodes, and then we can make sure that all the lanes are visited, that is cleaned. So here, and then we will run the algorithm provided in the MATLAB toolbox, and then with their giving of objectives, and then we can get a optimized route. So this and so applying these 3 steps on each region, and then we can optimize the route. And then next step, we also need to evaluate the performance of the 2 set of routes, the UDOT route and our proposed route. So here we selected 3 metrics to evaluate the performance of the route we obtained. The first one, the total travel times. That means the total vehicle means needed to clean all the lanes. For example, we can see this figure at the very beginning of time. The 4 trucks started from the depot marked with a blue square, and maybe about 1 hour later, 4 trucks finished their trips and they come back to the depot. So if we sum up all of the travel times of these 4 trucks, we know it should be about 4 hours. So we can say the total travel times is 4 hours. And then the next matrix is turnaround times. It means the duration of longest route. We still take these 2 figures for instance. Yeah, starting from the depot, and then after a duration they come back, and we can see the truck 1, truck 2 spend the longest times to finish their trip. It's about 2 hours. So this duration is the longest among these 4 trips. So we can see the turnaround times for this instance is about 2 hours. Okay, the last matrix we use is the dedicated miles. This can tell us maybe call it the utilization rate. So here means the total distance that the trucks travel without service. For example, we consider a road segment of length 1 mile. There are 3 lanes to be cleaned. And then, for example, these trucks takes 3 passes to clean all of the lanes, and then maybe he approached another lane and he had to traverse these lanes without service, and then this 1 mile can according dedicated miles. If we sum up all these such case together, when we get the dedicated miles for the whole network. So after introducing the 3 metrics, we will show the performance of these 2 set of routes in detail. And this figure shows the UDOT routes in terms of the 3 metrics. And the blue and the below one shows the proposed routes. And after comparison, we know that the travel time is reduced by 5% and the turnaround time is reduced by 15%, as well as the dedicated miles is also reduced significantly. It's about 50%. So based on this data, we can know that our our proposed route is much efficient than the routes implemented by UDOT currently. And also, I think this can save a lot of maybe working times and also maybe some investment in for the winter operation. So I think, this is the things I want to introduce for the snowplow route optimization. And next, we know and also here we want to show animation of the 2 set of route for Wells Wheel. Okay. Yeah. At the very beginning, there totally 4 trucks are allocated to Wells Wheel and it started from the depot and into different road segments. And we can observe that for truck 2 and 3, they have the same route, but the difference is truck 1 and truck 4. In UDOT route, the truck 1 started from the depot and go to north to the Newton and then go back, maybe have the refuelment, and then go to the east to complete the snow remover on the road in the canyon and then go back. This causes a very long turnaround times. So in our proposed route, we changed the road segments cleaned by the truck 1. He started from the depot and go to Newton and then go back here and then go back to depot and start again. But this time he didn't go to the road in canyon. He just go back and then go down and then go back to depot. And the rolling canyon is responsible is done by the truck 1. This way we reduce the turnaround times and we'll have more efficiency. Yeah. So these are the things we want to share with you for the part 2. And next, I want to talk about snowplow allocation. You know, there's a chance of the truck failure. So give a fixed fleet size. If we don't consider the truck failure, maybe it causes an increase in turnaround times. This has a bad impact on the service level. So in this part, we build up a snowplow allocation model. Yeah, we want to minimize the maximum turn times that can be sustained with the predefined probability. So the objective of this model is to minimize the T, and the constraint is that all of the truck we can use is equal to K, and also we make sure the maximum turn times across all the regions should be the probability of the maximum turn times across all regions should be less than T. Is less than T should be greater than 1 minus alpha. This alpha is our predefined parameter, and then 1 minus alpha is the predefined probability. And this parameter QR, XR minus CR denotes the turnaround times in our region. Assume that it was allocated XR trucks, but C trucks fails. And then if we assume that CR follows the binomial distribution, and we can compute the probability using these equations. Based on this, we can also rewrote our model in this format. Yeah, and this helps us to solve this model. And we propose a solution methodology that, as we mentioned, that the maximum turnaround times across 12 regions should be included in an infinity set. And with the data in this set, we can run the routing algorithm several times to get the turnaround times. So we first figure the largest T into this model and give and return this psi star. If the psi star is greater than log 1 minus alpha, and then we go to pick up a smaller T and then solve this model again. And before this constraint doesn't hold, and then we stop and return the Ti plus 1. Yeah, and also this model can also be rewritten at this format. This we can solve in games. Yeah. So applying this method, we solve our model. We can apply our model and method to the 12 regions and also involving 6-1 trucks. As we know that the QR function is a key parameters in our model. See, we run the routing algorithm with a varying truck fleet to get the turnaround times. The X is the number of trucks we used, and the Y-axis means the turnaround times. Yeah, for each region. Yeah, totally 12 regions here. And then this table shows we plug in we set different values alpha, and the method return the optimal solutions to our model. And then we can see we set the range, the range of the alpha values range between the 0.05 to 0.7. And then make sure different turnaround times can be sustained with the different probability. Here, we also build up a transportation problem to determine the snowplow reposition strategy to show how we can transform the current allocation to the resulted allocation with the minimal cost. Yeah, so in this, for example, this instance, we know that the region 1 should provide 1 truck to region 7, and the region 2 will receive 1 truck from region 8, region 5, and region 6, respectively. And besides, region 6 also need to provide 1 truck to 3. Yeah. So given this. Yeah. So this is the things I want to talk about the risk average snowplow allocation. Using this model, we can. I think this model is very useful to transportation agencies, especially the winter maintenance team. Yeah, for example, this model can determine how the allocation of the trucks to make sure to guarantee a certain service level. A level service can be sustained. Okay, and then we get to the final step, final part, the conclusion. Yeah, here in this presentation, I share with you 2 things. The first one is the snowplow route optimization. And we know that we optimize snowplow routes for 12 regions in North Utah. And we for these 3 metrics, all of them are reduced significantly. And this will help us to remarkably improve the efficiency of the snow removal operations, and I think also can recover the road conditions efficiently. And the second thing I talk about with you is the risk hour snowplow allocation. In this part, we formulate a risk hour snowplow allocation model and propose an iterative procedure to solve the model. And and then apply the model and the method to 12 regions in North Utah. Yeah, and then using this model, we can input any arbitrary value alpha to get the optimal solution to guaranteeing the service the turnaround times can be sustained with a predefined probability. So yeah, that's all for this presentation. Thank you for attention. Any questions?
So let me just jump in really quickly. Yinfu, I've shared the link for the 12 region animation in the chat box. So can you please perhaps open it so that the audience can see what all those routes look like? I shared it here, and so for the others also, if you look at the animation that Yinfu will share, you will see in the description of it the links to animation showing routes for individual regions. So we did a comparison at the region level, so you can see on the left-hand side the original routes, and the right-hand side the proposed routes.
Okay.
Nicola, you can share your screen if you would like. I gave you rights to do that.
Oh,
Yinfu, you've got it? Okay, he's got it.
Yeah.
Okay.
So basically, yeah, I can talk a little as well. So when it comes to representation of routes, we found it actually most effective to discuss them with the shed form and using these animations, because routes clearly overlap. So when you try to design a static visual of these routes, you can't really understand much out of it. So this is why we were going for these dynamic visualizations. Yinfu, can you also show some of the animations from the description, where show where they are, so that people can take a closer look at them afterwards?
So this is the proposed route, right? Only proposed route for each region. And I can see the description here.
So here you can see links for each of the 12 regions. Some of them also include different scenarios. So for some of the regions, Yinfu looked at the situation, well, what happens when we impose echelons on some of the major routes? What if we don't impose the echelons? What if we replace one single wing truck with a double wing truck? How does that affect the operations? Which is why for some of these places, you have basically multiple animations. Can you maybe open up North Logan, and then we'll of course invite the audience to explore these after the webinar.
Yeah,
So
yeah.
on the left-hand side, you have the original routes. On the right-hand side are the proposed routes. So this is how we're able to compare things apples to apples. The shed foreman loved this approach, and then you'll see basically on the right-hand side, our trucks or our routes will actually return to the depot, I think 15% sooner than the ones on the left-hand side. In other words, we're able to reduce the turnaround time by about 15% by balancing the workload among these different routes. So you'll see that the right-hand side will finish quicker than the left-hand side.
Yeah. Okay, so this is our work. Yeah.
I think you've paused it.
Go ahead. Go back. Yeah, this is working.
Yep. So with that, we can open it up for any questions.
All right, if anyone has any questions on the research, or maybe even how to dig in a little bit more and how they derived it, please go ahead and put your question in the chat or unmute yourselves and ask the question.
And these routes were implemented, so it was maybe a 15-month project that involved biweekly meetings with the shed foreman. In the case of some of the simpler regions, we were able to get the work done within just one or two meetings. For some of the others, like Centerville, you can maybe play Centerville animation that involved 9 trucks, and the road network was extremely complicated. In those cases, it took us over a month to prepare the routes.
So were you contacted by Utah DOT to help them with this with this effort, or was this an initiative that you guys kind of took on your own and then shared it with the DOT?
Great question. So we overheard that they had a couple of consultants, attempt to do this work, and they couldn't quite account for the different number of lanes and different operational constraints, types of vehicles, and so on. And it is definitely a fairly complex problem. So then we reached out to them. We told them that we did similar work in the past with different routing problems, and then they were excited to give us a chance. And I think they were pretty pleased with the results. So if you look at the vehicle miles, we brought them down by 5%. If you look at the turnaround time, which is a good proxy for the level of service, turnaround time was reduced by 15% of average.
Okay. Could this method be used to optimize future locations, in Utah's case, the depots or the maintenance sections?
Oh, that's a great question. So we, of course, have lots of constraints. Yinhu didn't go into too many details here, but for example, of course, you have the salt capacity, right, constraint. They're applying 250 pounds of salt or other chemicals per lane mile. And we thought that that would be a binding constraint. In other words, we thought that that would affect the routes. However, it turned out this was the case only for one shed. So in one shed, we saw that we could do better by basically adding one more salt pile. I think they call it like a satellite shed, so that the vehicle can actually refill along the way. And that helped, but only in one case. In other cases, the salt capacity wasn't really a binding factor. The fuel wasn't a binding factor, but we definitely went into this project thinking that we would perhaps we optimized the locations of those satellite sheds to a greater extent, but it turned out to be an issue for only one region. I think that was Lake Town, right, Yinhu, where we had one of the routes exceed 56 miles, which is the bound when you look at salt capacity. Great question. Yeah.
Have any other DOTs or public agencies reached out to you for assistance with their route optimization?
Not yet. We tried to go after some of the RFPs that were out by the Clear Roads initiative, but it seems that they prefer consultants over academia, so we haven't had much luck there. We talked to Colorado DOT, that were peripherally involved in it, but we still haven't been able to scale this work beyond Utah. At one point, the daycare is closed. That's fine. I have kids running around. But anyway, so the closest we got in conversations was with Colorado, but we didn't actually proceed with implementing. We're hoping to try to put together a pool fund study, so that's something that we may discuss with Utah DOT in the future.
Okay. I know that quite a few of the state DOTs, especially in our 4-state area, have been looking at this optimization plan and routing, and again the satellite locations for salt. So yeah, it's been a lot of work being put into this, or at least some consideration. So it's good that we have this information handoff so people can consider this as they move forward. So thank you for that. If anybody has any final questions, please go ahead and chime those in, and we'll try to answer those questions before we conclude.
One side comment, the same types of algorithms, or I would say the same type of problem arises in other applications, such as, for example, street sweeping or garbage collection or basically clearing roads after a hurricane or other natural disasters. So these are all the settings where you want to traverse all the road lengths or all the lanes of your road network. So there are lots of interesting applications here that go beyond snowplow routing. So just as an FYI.
Thank you. Well, it's not Friday yet, so but apparently they're excited to get out of here early. So I don't see any questions coming in. So thank you, Yinhu, for sharing this information, and Nicola, thank you very much as well for chiming in and helping out. Certainly appreciate it. Thank you, everyone, for attending today's TLN event. We appreciate your time and your attention. I sincerely hope you enjoyed and gained some new knowledge from today's session, and maybe have some resources that you can take forward to your teams to help them maybe make some decisions with your optimization and best effort, most efficient effort going forward. I encourage you to visit our website at translearning.org for upcoming learning opportunities and to access our learning management system. If you see a topic or anything out there that is of interest, please do share that with your peers so that they have the opportunity to attend some of the training as well. That being said, have a fantastic rest of your week. Be safe and don't forget to be awesome. Take care, everyone.